momenta. And this cone is actually defined as a graph of differential of some natural generating function for ground width invariance. The graph of differential using this polarization lives there. And it's a definition. But the fact that that graph of differential is a cone, it's a theorem about some identities for genus 0 ground width invariance, which I'm hiding from you. Now, if you want me to tell you, okay, so what is a generating function, I don't want to really spend time on that, but I can use this pictorial language somehow. So this, yeah. Yes.
What they are. So far, just decide that you use K0.
Yeah, I didn't tell you, because I'm saying I didn't tell you even how what are the interesting bundles that I'm using on the modular space of curves. I didn't.
Interesting bundles
No, I said that I define this way. You compute holomorphic characteristic of some interesting bundles on modular space of holomorphic curves, but I didn't tell you which bundles to take. Huh? No, any you can use it. It's Kawasaki milk. It's not interesting. What's interesting is when you take some particular bundles, but you give the answer what they're equal. You compute the answer. Okay, so I'm about to try to answer your question in some very general terms. So first of all, graphically, what's the generating function? I consider all kinds of curves with any number of mark points, right? So. Yeah, the first point is that, okay, so if you take a mark point here, maybe let's start with the following. So let's take, first of all, so let phi alpha be a basis in K node of X. So phi alpha some basis of bundles in there. Now if I pick alpha and pick an integer k and write phi alpha q to k, I'll get a Laurent monomial with vector coefficients in k. So therefore, I get this way I get a basis in this space k plus. So this is a basis in k plus. Actually, with every such a monomial, I can associate in every mark point. And if I pick a mark point in the curve, I can associate a vector bundle over modular space of curves. Namely this way. First of all, there is a cotangent line at this mark point, so cotangent line. So it's a sigma, cotangent line to sigma. It's a line, and therefore it defines a line bundle, let's call it L. Li if I is the index of the mark point. So line bundle over the modular space of curves, right? So there is a modular space. Each point there, it's a mapping of some curve to X. On the curve there is the mark point, cotangent line. It's gives you a vector bundle, a line bundle, and you can raise it to the power k. K stands the power, and also you see that point. There is a map of the curve to X, and that point lands somewhere in X, and over X there is this vector bundle phi alpha, and I can take the fiber of that bundle and consider it's a fiber of vector bundle over a modular space of curves, right? And this way, to this monomial, I have associated some element of K theory on the modular space of curves. Yeah, and tensoring. So when I take this, therefore this phi alpha, so for Q, I told you that's a universal line bundle. When I have a particular line bundle, I replace Q with that particular one, and so I'll get this phi alpha, if you wish, its evaluation at the ith mark point pulled back from X to the modular space of curves, tensor it with Li to the power k, and this what I can do at each mark point. And so if I tensor all these bundles together and then ask what's the holomorphic characteristic of these things, that's a k-theoretic ground width invariance. But now you should think for a second, what is a Taylor's formula? I'm thinking of generating function in the form of Taylor's formula. So Taylor's formula, it's a gadget that when you have, it says it's equivalence of two sets of data. One of them, you have partial derivative, that if we have collections of coordinate vectors which tell you in which directions you differentiate your function, right? And this collection of datum is equivalent to the following thing. Take a point in your space where these vectors are a basis and just compute the value of the function at that point, right? So I'm trying to convince you that this construction means that the natural generating function, so the function whose Taylor coefficients are all these numbers, is a function on K plus. So whenever we have a basis, so we pick several basis vectors in K plus, we have a number, right? And so this collection of numbers means that we just have Taylor coefficient of some function on K plus. Now I think we take graph of differential of that function and you'll get some Lagrangian section here. And the theorem says that that Lagrangian section actually turns out to be that it, not just some section, but it's a cone. But the vertex of that cone is actually not at the origin, it's somewhere off the origin, which is not surprising because a cone is not smooth thing. It's the graph of differential is a section, and the cone cannot be. It has a singularity. So really, the situation is that you have some formal function here, the generating function, and you take a graph of differential. It's a formal germ of some Lagrangian section. But the geometric properties of it is such that it consists of rays which, if you continue them, they meet at some point there. And so the situation becomes notation more convenient if you shift the origin. It'll make, so therefore that function actually, if I take that graph of differential and also shift it by some constant, so it'll make the origin sit here. So therefore that's what this that's how it arises. So it's a shifted graph of differential of that generating function whose Taylor coefficients are these holomorphic characteristics formed by these interesting bundles. Did I somehow at least vaguely answer the? Yeah, sure. Yeah, sure. Sure. In higher genus, yeah, I don't know how to understand better the symmetry. No, this part is, yeah. No, well, yes, no, these generating functions can be formed along all genera. So there is some generating function for each genus. Physicists tell us that we should think in this way. You should sum then we're putting Planck constants there and form such expressions. In other words, the physicists tell us that all genera together form some element of the Fock space, some quantization of some symplectic space. That's a symplectic space, that's that element. But what we're interested in genus 0, which means we pass to the quasi-classical limit h goes to 0, which actually, it should be object of classical mechanics. So it's not f naught itself, it's a differential of f naught, it's this Lagrangian so the object of classical mechanics, it's not a function, it is a Lagrangian submanifold somewhere. So therefore, I'm trying to convince you that it's natural to encode genus 0 information by some Lagrangian submanifold somewhere. But anyway, that's the object that we want to compute. Therefore, if we pick a point here. So now let me try to engage this bookkeeping device and just tell you just slightly more how a point on that cone looks like more or less by definition. So that point has, as any point in the space, has first of all projection here to k plus, and then a projection here to k minus. And as I told you, it's a graph of differential of some function that we want to compute, which means the following. So what is here, this projection specifies the equation. It tells us what we want to, what we're asking, what's the equation that we're asking. And this gives the answer, right? It's a graph of some interesting function. So more accurately, it looks like that. So it starts with this term, which is exactly that quantity by which I shifted. The actual origin of that cone would be in the point q minus 1. And somehow universal answer. So actually shifting the origin, I shift all vectors by this. Therefore, that point in the cone looks like that. So there is 1 minus q plus there is some Laurent polynomial in QQ inverse, and then again using my graphic device, I could say this. So therefore, if I ignore that picture, so but just look at the definition of my object, that's how it looks like. So you see that there is that shift. Then there is some Laurent polynomial of Q, which I actually use to form a bundle at each mark point. So that's how my generating function looks like. I put it just computes in sum over all possible curves, and putting at the mark point some point by vector space. But I took the differential. It means that I differentiate this function in one direction. It means that I singled out one mark point. And that's convenient because that's what exactly we can understand better. So, and let's denote it as a horn. And therefore, that's how my thing looks like. This is part in K minus, and then it determines the equation that determines what I put into the what I use as bundles, whose order characteristic I compute. And this picture means that I take the sum over all modular spaces of all the corresponding holomorphic order characteristics to produce the answer. And this should lie in K minus. And actually should lie in, it should be an infinite dimensional vector because I differentiate in every direction, coordinate direction, so I put infinitely many choices here. But if you think what it means in terms of this loop space notation, it means the following. What I should put at this point, I should put at the horn 1 divided by 1 minus QL. So therefore, that's how, by definition, a point on my cone looks like. It is some part which is in K plus, or it's K plus, and that's part in K minus, and it depends on Q only through this mark point, and so on. It's time to stop. Okay, so now maybe I will tell you in. So therefore, what happens next? We use this part and now replace it with this representation by Kawasaki-Riemann formula. So our formula now looks this way. So a point on the cone is 1 minus q plus this Laurent polynomial plus contributions of this strata from Kawasaki's formula. And so the only change that I need to make now, I now know what I put here at the horns. So there is so in the Kawasaki formula, I should replace this L with, I should use eigenvalues, so there will be QL eta here, and okay, that's how the picture looks like. Therefore, this plus that plus all of that, that's all the things that Kawasaki-Riemann formula tells me is that my sum will be represented, my invariance represented this way. Now, so what's the theorem? Okay, so this is C minus 0. It's the plane where Q lies. And over each point eta here, so actually the form of the theorem is like that. So a point lies in that Lagrangian cone if and only if its Laurent expansions at all points. So if I take collection for all eta not equal to 0 and infinity, and consider Laurent expansions of that rational function there, then it must lie in a particular cone corresponding to that's eta. So what's happening here is the following. Over each point eta, there is sort of, it's an adelic description, if you wish, of that cone. So over each point eta, there is this space, let's call it k eta, which is a Laurent series with vector coefficients of 1 minus q eta. So Laurent series which have pole at q equal to eta inverse only. In particular, there is 1. Here there is unit circles and roots of 1 of all kinds, and etas which are not roots of 1. And I need to describe what all the things are, and the statement, one statement is that if eta, so eta is not a root of 1, not a root of 1, then this thing L eta is just sort of k eta plus. So it means that the function has no pole at that point. And you can see this from this expression. So in this expression, the only poles where this function can have, so L is unipotent here. L is a line bundle which is approximately 1. And so therefore this expression can produce poles only at q equal to 1, and here only at q equal to eta inverse. And no other poles are possible. Then if k is equal to 1, if eta is equal to 1, then in this space K1, there is some cone which corresponds to actually to this theory. It's what we call, it's a cone of the fake K theory, which means that we I started describing this Kawasaki-Riemann formula by just starting with writing down the usual term, the usual Riemann formula. So if we take for definition of holomorphic Euler characteristic on an orbifold, just the integral of the product of the Chern character and the Todd class, ignoring all the other strata, then it's a fake holomorphic Euler characteristic. It's a wrong one. It gives a rational number, but it can be computed in terms of homological curvature more successfully. And so over at equal to 1, it's exactly that cone of that theory that lies there. So it's the corresponding Lagrangian section of that theory. And over all roots of 1, there is actually that cone becomes not a cone, it's some subspace, which also can be explicitly described in homological terms. So therefore, the structure of the answer is like this, that which there is map from k to the product of k eta adelic space, and the cone here is mapped to the product, and that's a theorem. It's mapped to the product of corresponding subspaces or cones there. Those are explicitly described in homological terms. It's a different story, but that's the theorem. So the point lies here if and only if it passes this test of belonging to corresponding n eta when it's expanded in powers in Laurent series at every point on that plane. And if I take maybe 30 seconds, I will try to convince you by staring at this picture about my statement at eta equal to 1. But you should exercise your imagination. So you see that just this picture, what does it tell, this information, what does it tell me? So there is this kind of 1 minus q, there is this Laurent polynomial, and this means contributions of all strata of this type into what I'm computing, this contribution of all strata of this type what I'm computing. And but I claim that this picture tells me that this thing lies on the cone of the fake theory. So what's the cone of the fake theory? In the fake theory, what I have 1 minus q plus some Laurent series in q minus 1. Power series. Power series in q minus 1. So anything that has no pole at q equal to 1. Plus this fake invariance where this power series is used as an input at every mark point, if you wish. So, but it's a fake, so it means that it doesn't take into account any symmetries of curves, just integral all curves. And here I have 1 minus QL. Now look at this expression. Okay, this is the part where I don't take into account symmetry, so this is space. Now, in a way, kind of, I'm stacking at each mark point. I declare these things, which are, well, there are mark points here, but there are the singular points. I declare them mark points on my modular space, but then I stack something there, some ingredients. And so what exactly can be there? One choice, it could be a mark point, which means it could be this thing. But it could be any curve like that, except that the eigenvalue here could not be equal to 1. And on my picture, that's what it is. So this is the sum of all expressions, depending on Q, where the eigenvalue is not equal to 1. And so therefore, if I take that thing and this thing together, all of that, and denote it T tilde, which will be an expression which has no pole at 1. It's a power series in Q. Poles at roots of 1, but not at Q equal to 1. Then exactly that expression where I substitute L for Q is what I insert here at the mark point. Right, so because it's either just the content of a mark point, or the result of what I get here. So instead of this Q, I need to substitute this line bundle. So just stating in this picture, you already see that it tells you that if you take your rational function and expand it at the pole Q equal to 1, that the result will lie in the cone of the fake theory. And likewise, you need then process all other, so you need to analyze what happens here, and so then you write this kind of theory. Thank you.
Thank you very much for your talk. I'm afraid we're completely out of time. So if you have any additional questions, we'll move now over to the Math Commons room for our refreshments. So thank you once again.
Thank you.